Can the Schrödinger wave equation be interpreted as supporting the existence of the ether? While in all energy equations involving frequency, there is a direct proportional relationship between energy and the square of frequency, why don't we see this in the E equals hf equation? Unlike the others, this equation is directly proportional to frequency. In systems involving radio waves, sound waves, simple harmonic motion, and many others, the energy associated with the system is directly proportional to the square of its frequency. This quadratic relationship is a fundamental principle in various areas of physics. These equations demonstrate the relationship between energy and frequency in simple harmonic motion. As seen, when the coefficient k is increased fourfold, the frequency doubles, but the energy quadruples. This indicates a direct proportional relationship between energy and the square of the frequency. Radio waves also exhibit analogous behavior. The Friis transmission equation, a cornerstone in antenna theory, quantifies the power transfer between transmitting and receiving antennas. In this equation, PR denotes the received power at the antenna, and PT signifies the transmitted power from the source antenna. Given the relationship between wavelength, frequency f, and the speed of light c, the Friis transmission formula can be reformulated in terms of frequency. A doubling of the frequency at the transmitting antenna necessitates a quadrupling of the transmitted power PT to maintain a constant received power PR at the receiving antenna. Although radio waves and light are electromagnetic waves, the relationship between energy and frequency is different. We cannot apply the E equals hf equation to radio waves. The table presents a comparison of the energy requirements for 2.4 GHz and 4.8 GHz radio waves over an identical distance. It is evident that to transmit a signal over the same distance using a frequency of 4.8 GHz, a power of 400 milliwatts is necessary. This indicates a quadratic relationship between frequency and required power, where doubling the frequency results in a fourfold increase in power consumption. In table also, we observe a directly proportional relationship between energy and the square of the frequency. A similar relationship can be seen when studying sound waves. The intensity of a wave is defined as the power emitted by the source divided by the surface area. You can see that the intensity is directly proportional to the square of the frequency. The only energy equation that is not directly proportional to the square of frequency is E equals hf. But why? Let's take another look at how Planck discovered the equation E equals hf. After the interference and diffraction experiments related to light, physicists agreed that light was a wave. James Clerk Maxwell's brilliant unification of electricity and magnetism greatly reinforced the idea that light was an electromagnetic wave. By the 19th century, the particle model had already been abandoned. For this reason, all mathematical models related to light were based on wavelength and frequency. The problem referred to as the ultraviolet catastrophe was also approached this way. The idea that heated objects emit electromagnetic waves had been widely accepted. In other words, the prevailing thought was that the emitted energy was in the form of waves. While explaining the ultraviolet catastrophe problem with energy packets, Planck established a relationship between the energy of the packets and their frequency. The intensity wavelength graph was already based on this assumption. Planck also thought of the energy packets in waveform. However, he did not provide any proof that these energy packets had a frequency. He simply associated them with frequency, relying on the prevalent belief of his time. There is another structure that aligns with Planck's energy packet model. Doublets formed in an ideal gas environment. We can consider the doublet formed in an ideal gas environment as flow lines in the shape of concentric circles passing through the same center. Let's consider a small volume on any flow line. Assume that there are n particles within this volume and that the particles are moving inside an imaginary cube. From the perspective of an observer moving with the flow, 1/3 of these will collide with the walls along the x-axis, One-third will collide with the walls along the y-axis, and one-third will collide with the walls along the z-axis. Let us assume that the flow is in the positive direction of the x-axis. The root mean square velocity of particles is a vector sum of its x, y, and z velocity components. Above is the combination of x, y, z velocity components of the RMS velocity of particles. The RMS velocity of any particle is equal to one of these combinations. As can be seen, half of the particles in this volume are moving in the same direction as the flow, that is, in the positive x direction, while the other half are moving in the opposite direction. The velocity components of the particles along the e, y, and z axes are perpendicular to the flow. Let's calculate the speed of the particles relative to a stationary observer. The velocity of a particle moving in the same direction as the flow is called v1, while the velocity of a particle moving in the opposite direction is called v2 in equations. Since half of the particles have a velocity of v1 and the other half have a velocity of v2, we multiplied by n divided by 2. If we add equation v1 and equation v2, we get the equation above. Since the magnitudes of the velocity components are equal in all directions, we added up the velocity components. We can define the square of the RMS velocity as equal to 3 times the square of vx. If we substitute vrms squared in place of 3 times vx squared in the equation, we obtain the equation displayed on the screen. Let m be the mass of a point particle. By multiplying the equation by 1/2 m, we obtain the total kinetic energy of the gas inside the cube. If we denote the average kinetic energy of a single particle as epsilon, then the total energy of n particles is n times epsilon. From this, we can derive the equation for epsilon. Epsilon represents the total energy of a single particle. The value of m is the same and constant for all the particles that make up the ideal gas. Since energy is conserved, the sum of the squares of the flow velocity and the square of the RMS velocity is constant. As the flow velocity increases, the value of RMS velocity decreases in equation. Since epsilon is the kinetic energy of a particle, the masses m and the 1/2 terms cancel out, leaving only the velocities. Kinetic energy of particle also represents the temperature. In this case, the relationship between energy, flow velocity, and temperature is revealed. Now let's examine the relationship between temperature and density. We can find the density equation using the ideal gas law under constant pressure. If we rewrite the density equation, we can see that the product of temperature and density is constant under constant pressure. If we combine the equations for kinetic energy and temperature with the density equation, we obtain an equation that shows density is dependent on the RMS velocity. If we express the wave function in terms of the RMS velocity, the density can be represented as an equation in terms of wave function. If we replace the RMS velocity function with ER, we obtain the following density graph. The radial density graph is as seen. The radial density graph for the other VR function is as on the screen. And here is the radial density graph for another function. As seen, the resulting density and radial density graphs overlap with the density and radial probability graphs of the hydrogen atom. Schrödinger equation and heat equation. Let's consider that space is not empty, but rather filled with an ideal gas that is completely frictionless and has no viscosity. This gas is not composed of atoms or subatomic particles. It consists of particles that are smaller than quarks, representing the smallest building blocks of the universe. All particles that make up a gas have the same mass and kinetic energy. We will assume that the kinetic energy of the particles is 6.626 times 10 to the power of negative 34 joules. In fact, we will consider that Planck's constant is a value that gives the kinetic energy of the one particle that make up the ideal gas. This value represents the smallest unit of energy in the universe, meaning it is the kinetic energy of a single particle that constitutes the ideal gas. Suppose that all the subatomic particles in the Standard Model are doublet structures that occur in this ideal gas environment. In this case, the probabilities of subatomic particles' existence will be the same as the density of the ideal gas. As the density increases, the number of particles will increase. Since the energy of each particle is equal to the Planck energy, an increase in density means an increase in energy. Since density is dependent on temperature, the density graph will also be temperature dependent. This is actually a heat problem. Therefore, Schrödinger's wave equation is essentially a heat equation. The heat equation has a first-order partial derivative with respect to time. The Schrödinger equation also has a first-order partial derivative with respect to time. In contrast, the wave equation has a second-order derivative with respect to time. As seen, the Schrödinger equation is not a wave equation, but rather a heat equation. When we compare the diffusion coefficient alpha in the heat equation with the Schrödinger equation, we find that the equivalent of alpha in the Schrödinger equation. If we do a unit analysis of the diffusion coefficient alpha in the heat equation, if we do the unit analysis of the coefficient in the Schrödinger equation, as can be seen, the units of the coefficient in the heat equation and the coefficient in the Schrödinger equation are the same. This is solution of one-dimensional heat problem of length L with boundary conditions. And this equation is actually the one-dimensional solution of the Schrödinger equation for sine function. The solution of the heat equation and the solution of the Schrödinger equation are the same. Frequency of energy packets. Let's consider how the total energy of the doublets changes quantized. Assuming that the doublet consists of n particles, its total energy is n times epsilon. As seen, the energy of the doublet increases quantized in multiples of epsilon based on n. Let us think of the electron cloud surrounding the atomic nucleus as a doublet formed in an ideal gas environment. If the electron is a doublet, the rest mass energy of the electron is equal to the total kinetic energy of the particles that make up the doublet. If we say n is the number of particles that make up the doublet, since the mass of the electron is equal to the mass of the doublet, the masses are simplified and the velocities remain. We previously mentioned that the sum of the squares of the flow velocity and RMS velocity is equal to the square of the particle's total velocity. Assuming the flow velocity is 0 at a sufficient distance from the doublet center, the RMS velocity of the particles making up the ideal gas reaches its maximum value. When the flow velocity is 0, the value of 2c squared is equal to v RMS squared. You may object to the VRMs of particles being higher than the speed of light. Let's think of this situation as follows. Each fluid has its own wave speed constant. For example, the wave speed constant of air, the speed of sound, is 343 meters per second, but the RMS speed of oxygen molecules is 478 meters per second, and the RMS speed of nitrogen molecules is 511 meters per second. The VRM's value of the particles that make up the gas is always greater than the wave speed constant. We have already mentioned that the energy of a particle is 6.626 times 10 to the power of minus 34 joules. Since we know the velocity, we can calculate the mass of the particle using the kinetic energy equation. Now that we have calculated the mass of a particle, we can determine how many particles make up an electron. If the electron consists of n particles, we can find this by dividing the mass of the electron by the mass of the particle. We have determined how many particles make up an electron. This value may seem familiar to some of you. As you know, an electron and a positron come together and transform into two gamma rays. The frequency of the resulting gamma rays is 1.237 times 10 to the power of 20 Hz. It has the same value as n. As seen, two different perspectives lead us to the same conclusion. We can also substitute the number of particles for frequency. Considering that the relationship between frequency and energy is proportional to the square of the frequency, the equation E equals hf would be a problematic equation. If we add spin to the doublet, we get a vortex like on the screen. This vortex has three properties that allow subatomic particles to be identified. These three properties are mass, spin, and electric charge. A vortex is a sink when viewed from above, and a source flow when viewed from below, or vice versa. Schrödinger versus Bernoulli. While all flows are compressible, flows are usually treated as being incompressible when the Mach number is smaller than 0.3, since the density change due to velocity is about 5% in that case. The Mach expression for vortex flow is equal to the speed of light. In other words, until the flow speed reaches 0.3 light speed, the flow is incompressible flow and acts according to the Bernoulli principle. The region where the flow acts according to the Bernoulli principle is the region where the electromagnetic force is generated. When the flow rate exceeds 0.3 Mach, the gas is considered as a compressible gas. This is the isobaric region. In other words, the pressure is equal everywhere. Because the pressure in the Bernoulli zone is higher, inward compression occurs and the internal pressure is balanced. As the pressure is balanced, the density increases. In this region, a probabilistic particle is formed, expressed by the Schrödinger wave equation. We can call this region the Schrödinger region. The figure shows the tangential velocity plane of the flows in the Bernoulli region for the vortex. Radial flows are neglected. View from above. Two vortexes approaching each other enter each other's Bernoulli zone. As a result of the superposition of two flows in the same direction between the vortexes, the flow velocity increases, and according to the Bernoulli principle, the pressure decreases where the flow velocity increases. This causes them to approach each other as if there is a pulling force between the two doublets. This is how the attraction of positive and negative charges takes place. When opposite directional flows meet, the flow velocity decreases and the pressure increases according to Bernoulli's principle. This causes the doublets to act as if there is a repulsive force between them and move away from each other, a situation where the same charges repel each other. As we have seen, there are thought-provoking analogies between fluid mechanics and quantum physics. It seems that our universe is filled with an ideal fluid gas, and it is this gas that generates the particles and force interactions in the Standard Model. In the 1970s and 1980s, the Bulgarian physicist Stefan Marinov conducted a variety of coupled mirror and tooth wheel experiments to measure the one-way anisotropy of light and measured an absolute ethereal motion of roughly 300 kilometers per second. This speed coincides with the speed of the Milky Way galaxy. But how do we explain light's interference in the double-slit experiment and other wave properties? I have answered all these questions in my article, the link to which I have added to the explanation below.